Now let us solve another university question from May 2019 supplementary examination. 12th question, which carries 10 marks. So, design a digital Butterworth filter satisfying the constraints, this one, with t equal to 1 second using bilinear transformation. And the scheme of evaluation is given as pre-warping 1 mark, order and cutoff frequency 3 marks, calculations of h of s 2 marks, transformation equation 1 mark, then substitution and final answer 3 marks. And the final answer is also shown here. First you read the question carefully. Here we can see where to design a Butterworth filter. The specifications given are in digital domain and we have to apply the bilinear transformation for the digital to analog and analog to digital transformation. So if you have practiced previously this type of questions, you can easily solve such type of questions. Only thing is you should be careful while computing each steps. So let us try to solve this problem. The given specifications are 1 by root of 1 plus epsilon square equal to 0.9, from which we can easily compute epsilon as 0.4843 and 1 by root of 1 plus lambda square equal to 0.2, from which lambda equal to 4.9. As you know, this 0.9 is the passband ripple and 0.2 is the stopband ripple regions. So corresponding to 0.9 we have the passband edge frequency omega p, which is given as pi by 2, and the stopband edge frequency omega s equal to 3 pi by 4. Since the filter designing transformation is based on bilinear transformation, you have to apply the pre-warping expression for converting this digital frequency to the analog frequency. And the pre-warping equation, we know it is given by capital omega equal to 2 by t tan omega by 2. So in our case, t is given as 1 second. So therefore we can obtain omega p as 2 tan pi by 4, which is equal to 2, and omega s equal to 2 tan omega s by 2. So computing we will get 4.8284. Next step is the determination of capital N, the order of the filter. N is given by the expression logarithm of lambda v epsilon all divided by logarithm of omega s by omega p. When substituting and computing, we get the value as 2.6257. So in the next step, we have to determine the value of capital N by rounding the value to the next highest integer. So in this case, we know it is equal to 3. So the order of the filter capital N equal to 3. So we got N equal to 3. Next step is the determination of the normalized transfer function, which can be either taken from the lookup table or you can compute using the equation. So you can choose the normalized transfer function from the table corresponding to 3 as 1 by Sn plus 1 into Sn square plus Sn plus 1, or you can compute the same using the general equation, which is given by, for if n is even we can use this one, or if n is odd we can use this one, where bk equal to this one. So in our case n is odd, which is 3, so we can use the second expression. We are using the equation for computing h of Sn. You can apply this one corresponding to n equal to 3, and if you are substituting n equal to 3, it will be 3 minus 1 by 2 means it will equal to 1. Then bk is given by this expression. If you are substituting b1 equal to 2 sine pi by 6 is equal to 1. So the h of Sn will be 1 by Sn into this step. So that you will get the equation like this. So once we have the normalized transfer function, the next step is to transform the given normalized transfer function to the actual cutoff frequency. So in the next step, we have to determine the cutoff frequency of the filter. Once we have the cutoff frequency omega c, then the corresponding transfer function h of s can be obtained by simply replacing each Sn with s by omega c. So let us compute the cutoff frequency omega c. Here the omega c can be computed either using the passband edge frequency or the stopband edge frequency. So there is a slight difference in the values when we use both these expressions. So Ramesh Babu's textbook follows this omega p by, whereas the Nagurkanik's textbook follows the omega s by lambda raised to 1 by n. Actually, the better performance is by the cutoff frequency corresponds to the stopband edge frequency. And MATLAB also by default follows the omega s by lambda n expression. But in this particular case, the final answer is based on this omega p by epsilon raised to 1 by n. So let us follow with this equation. Depending upon the omega p or omega s, there will be a slight difference in the final answer. So in our case, we are following omega c equal to omega p by epsilon raised to 1 by n, which is equal to, so substituting the corresponding values and computing, we get the cutoff frequency as 2.5467. So next step is to replace every Sn with s by omega c. So substituting, we get the expression in this form. Now after simplification, we get h of s obtained as 16.52 divided by s cube plus 5.093 square plus 12.97 s plus 16.52. So we have determined the analog transfer function. So the next step, we have to transform the analog transfer function into the digital domain by the bilinear transformation. So that we will get h of z. By using bilinear transformation, h of z can be obtained as h of z equal to h of s at s equal to 2 by t 1 minus z inverse all divided by 1 plus z inverse. So here t is the sampling period. So in our case, t equal to 1 second. T equal to 1 second, and substituting and simplifying, we get the equation or the final answer as h of z equal to 0.2332 into 1 plus z raised to minus 1 all raised cube all divided by 1 plus 0.4394 z raised to minus 1 plus 0.3845 z raised to minus 2 plus 0.0416 z raised to minus 3. Or in another form as 0.2332 z cube plus 0.699 z raised square plus 0.6 in this form also. Both these results are one and the same. So we have the final answer here.